Thanks everybody for coming tonight. I want to keep this informal. Ames is a family. We're not an institution. And in families, everybody is free to speak at any time. So please interrupt, ask questions, make complaints, criticisms, whatever moves you, feel free to say. So first of all, a big thank you to all of you for coming, for being here, for representing the whole of Africa in one small institution that is trying to change the world. So I'm going to talk about this, about science and our future. But actually, the main point of my talk is to talk about Ames and the future of science in Africa and Africa's future. So let me just begin by telling you about the special time we live in. We live at a special time in human history. Why? Because human beings have learnt more about the universe, about everything, than we ever expected to. And it's not like we understand everything. There's still very big mysteries, but the one thing we've learned is that the human mind has this astonishing capability to make sense of nature in realms way beyond everyday experience. And that ability gives us an opportunity that we can control our destiny and we can control the fate of humankind and the future. So I'm just going to give you a few examples from physics, of course. I'm a physicist, I'm a cosmologist, but there are many other examples of incredible achievements of technology and science in just the last few years. So I'm happy to talk a little bit about those too, but I'll just begin by talking about physics. So in the last 3 years, we have learned more than in the previous 3 decades. It began with the discoveries of the largest experiment ever conducted, the Large Hadron Collider, which you can think of as the most powerful microscope ever built. It's capable of seeing the smallest things. And then shortly after that, 1 year later, was the Planck satellite, which is the most powerful telescope ever built that can literally see the whole universe in visible radiation, in electromagnetic radiation. And so in these last 3 years, we've seen the smallest thing, we've seen the biggest thing, that's the biggest thing, the whole visible universe. I'll explain a little bit later what this picture means. But you should think of this as a map projected onto a plane, but it's really a sphere. We live inside a spherical surface. That surface is 14 billion light years in radius. And on the surface of the sphere that we live inside, we can see these small fluctuations. And these small fluctuations are our ancestors. Okay, those fluctuations later gave rise to galaxies, stars, planets, people, and everything around us. So they're very important. And there's strong indications, by the way, that these small fluctuations are quantum in nature. We used to think that quantum applied only to the atom, but this data indicates that quantum applies to the whole universe. So that's a great thing to think about, and I may talk more later about it. The smallest thing is the Higgs boson. By the way, this visible universe that we see, this sphere that we live in the middle of, is 10 trillion times larger than the solar system. Okay, so I don't have any chalk here. Here we are. Right, 10 to the 13, 10 trillion times larger than the solar system. It's pretty amazing that we can understand nature on that scale, okay? But the theories we have, the interpretations we have of this data are incredibly simple. In fact, they're more accurate than any model of, let's say, financial mathematics. Okay, we can understand this picture with beautiful precision, and it was predicted that we would see this pattern by the simplest theories long before it was measured. So the human mind is capable of predicting and understanding things on this size bigger than the solar system. Okay, which is a pretty big place. Now, we've also seen the Higgs boson. The Higgs boson is the smallest particle we know. It's not important that it's a particle. The Higgs boson is really like a ripple like a sound wave in water. Imagine we are all fish living in the sea. We're moving through this medium. This medium controls how quickly we can move, right? Because we have to displace the water. Well, when we move through empty space, we're actually moving through the Higgs field. It fills all of space. And it endows particles with their mass and electric charge. It tells the particles what is their mass and charge. It's a very fundamental thing. So the Higgs field fills all of space, but if you excite it, like I'm exciting the air in this room by speaking, and then something travels through the air to your ears, well, the Higgs boson is an excitation of the Higgs field that fills all of space. The boson itself is tiny. It is about 1/billionth the size of the atom. Okay, so our best microscope can see 1 billion times smaller than the size of an atom. That's pretty amazing. And so human beings have somehow managed to, by the way, just as I said, we can actually understand many features of this map of the universe very precisely. In the case of the Higgs boson, this was predicted 50 years before the experiment on the basis of mathematical reasoning. Okay, a beautiful paper by Peter Higgs, 1.5 pages long. Okay, explained about the Higgs field and the Higgs boson and predicted the particle. And when it was seen 50 years later, after a 10 billion euro machine was built, it fits perfectly with Higgs theory. I'm going to tell you about an even more spectacular prediction which happened just this year. So we're not only interested in measuring very big things and very small things, we're interested in measuring very accurately, very precise. And in fact, the precision frontier of physics is becoming even more important than the distance frontiers, the big and the small. So the most accurate measurement of length ever made is by this advanced LIGO experiment. Have you heard of it? Has anyone heard of it here? Most have not heard of it. Okay, it's a telescope, and what it consists of, there are two independent telescopes. Each one is 4 kilometers long, and each one is a right angle. So it has two arms, 4 kilometers long, at right angles. Do you know what it's designed to detect? It's not measuring light, it's not measuring radio, it's not measuring anything electromagnetic. What is advanced LIGO detecting? Gravitational waves. Okay, so gravitational waves were, it's not fair, they're cosmologists. Gravitational waves were predicted by whom? Einstein. I think about 1916. Einstein, maybe 1915. Einstein worked out how gravity works, right? So the reason we are held on the floor is because of gravity. Einstein made a theory of gravity which replaced Isaac Newton's theory of gravity as the explanation for the gravitational force. And Einstein realized that at that time that his theory would predict waves. Just as light is an electromagnetic wave, gravitational waves are waves in space and time. So they're distortions of space where literally the length between 2 points in space will change if a gravitational wave passes by. Now, Einstein did this 100 years ago, and he was very discouraged because gravitational waves are very weak. An ordinary body in motion hardly emits any gravitational waves. In order to emit gravitational waves in significant amount, you have to have a big mass moving extremely fast. In fact, it has to be accelerating extremely fast. And so Einstein worked out how strong gravitational waves would be and how detectable, and he was very disappointed. He thought they're too weak to ever be measured. But here we are 100 years later, and we can measure them. By the way, these experiments took 50 years to design and implement with a team of over 1,000 physicists and many engineers. These are incredible achievements. So what LIGO does is very simple to explain. It's a 4-kilometer long arm, and what they're trying to do is measure its length very precisely. And they measure its length to an accuracy better than 1/10,000th the size of an atomic nucleus. Okay? An atomic nucleus is quite small. It's 10 to the minus 15 meters. Okay? And they're measuring the length, this 4-kilometer arm, to an accuracy of 1/10,000th of that. So 10 to the minus 19 meters over a 4-kilometer arm. If you ask me to explain how they do it, it will take a long time. It's very subtle. It uses quantum effects. It uses lasers and light. But this is an astonishing telescope looking for a tiny, tiny effect. Literally, if you go near that experiment and just go like that on it, you will completely destroy their data. Okay, they're very sensitive. In fact, this one is in a forest. And when people chop down a tree, they can see individual tree falling in the detector. So it's very difficult. Now, what they saw, and this was announced in February this year, is this amazing result. Okay, so I call this the discovery of the century. It took 1 century after it was predicted. Now you can't see this very clearly. Let's turn that light off if we can. Can I turn it off here? Can I turn this light off? There we go. So I don't know if you can see this either very well. Can you see it? Okay, let me rewind that. Okay, so if you look on the top of the picture, you're going to see space, which is distorted. This is a picture of the bending of space. Above are the 2 black holes. They're orbiting each other. And these 2 black holes emit gravitational waves, lose energy, approach each other. And when they approach each other, they merge into a single black hole. The plot here shows the signal in the instrument. Okay, so this is the predicted signal according to Einstein's theory, which is that one of these arms is going to get shorter and longer, and the other arm will get shorter and longer, but in the opposite way. So if this one gets shorter, that one gets longer, and so on. So it goes up and down, the length of the arm, and then it increases in strength, and the frequency gets shorter, and this is called a chirp. This is the chirp of gravitational waves emitted by the two black holes as they get faster and faster and then merge into one. And you see these things going out, those are the gravitational waves. This pattern here. These are ripples in space which travel through the universe. And so the detection here, I won't show you the data, but it's absolutely spectacular. The data agrees beautifully with the theoretical prediction. There's no, it agreed much better than the experimentalists expected. In fact, their first worry when they saw the data was someone had cheated. They suspected somebody had hacked into their computer and deposited this data because it really was too good to be true. And so they spent about a month trying to exclude the possibility that somebody had hacked their computers and inserted the data. It's absolutely spectacular. And then about a month ago, they announced the second event, another black hole merger. Now, what is amazing about this is this event happened 1.4 billion light years away from us. Okay, it has taken, you can tell that from the strength and the shape of the signal. You can determine the masses of the black holes. You can figure out how strong was the gravitational waves when it's emitted. You know when it was measured, and so you can work out how far it was away. 1.4 billion light years, and it took about 1/10 of a second, the whole thing. Okay, so they came in and did this 1.4 billion light years ago. The gravitational waves came through space. They've been traveling ever since then. They've been traveling for 1.4 billion years. So they were emitted before human beings existed. And they've been traveling ever since. And then in 0.1 of a second, they came past and were detected. And they agree with our theories. So they were emitted long before there was a theory. Long before there was even a living organism. Actually, there were some very primitive living organisms on Earth 1.4 billion years ago, but not any sort of advanced life. So this is where we've come. Theoretical physics has this spectacular achievements, but much more than that, we now have the eyes to see the whole universe. And actually what makes me excited, we have the possibility of seeing what happened at the Big Bang itself. The Big Bang is where everything came from. And it's one of the fundamental questions in physics. What happened at the Big Bang? What caused the Big Bang? That's where everything comes from. With ordinary radiation, like electromagnetic waves or light or radio waves, we can only see back to 400,000 years after the Big Bang. Any earlier than that, and the universe is opaque. Light cannot go through it. But gravitational waves can travel straight through, and we can see what happened at the Big Bang. So this is our world, this is our universe. We live here in the solar system. And the radial scale on this picture is logarithmic. Okay, if you take the logarithm of a scale, it makes big numbers small. And so, the solar system looks fairly big in this picture just because it's been blown up relative to distant objects. And as we go out in radius, we go backward in time. because we're seeing the universe as it was when the light was emitted. And so we see the time when galaxies formed. We're currently at 14 billion years after the Big Bang. This is at times like 5 billion years after the Big Bang that galaxies formed. And going back further, we can see the beginning of structures forming in the universe. This is called the cosmic web. And going back to the red ring, that's when the light and the radiation, the electromagnetic radiation that we detect now was emitted. That was 400,000 years after the Big Bang. And if we go outward to the gray ring is the Big Bang itself. And as I said, using electromagnetic radiation, we can look all the way back to the red ring. Using gravitational waves, we can see back to the gray ring. And that's going to happen. In the next few years and decades, we will have telescopes which enable us to see what happened at the Big Bang. This is our story, the story of the universe. It began somehow, we don't know how, but we make theories. I make theoretical models, and we try to test them against data. This is the formation of atomic nuclei and atoms. We can calculate how that happened. We can predict the abundance of the different chemical elements in the universe. And then we form galaxies and stars and planets. And then you notice at recent times, after about 10 billion years after the Big Bang, the universe starts, so time goes this way, size is this way, and so about 10 billion years after the Big Bang, the universe starts to accelerate in its expansion. It's getting bigger, faster these days because of something called dark energy. And we don't know what it is, we don't know how to explain or predict it, but we can model it very simply. And it's probably the biggest problem in physics to understand what is the dark energy. But space is full of energy, and it may be that one day we can even use that energy. There are various indications from discoveries at the Large Hadron Collider that energy may be accessible. And if so, we may be able to travel to other galaxies throughout the universe. So this is speculative, but personally I believe that's likely. And if we go far into the future, the world is very strange. The world becomes dominated by dark energy. All the galaxies are diluted away by expansion. The dark energy remains. And it's a big puzzle. Where is the universe going? It seems to be going to a strange place. Okay? And yeah, actually, I'll tell you a story. If anyone asks me afterwards, I'll tell you a story about the Prime Minister of Canada and the question he asked about the dark energy. But anyway. So, yes, go ahead.
Is there a relationship between the Higgs boson and gravity?
Yes, there is. So, according to the standard model of particle physics, the Higgs field, which is like the electromagnetic, the Higgs field, so the Higgs field is something which is present everywhere in space. According to the standard model of particle physics, the reason the Higgs field is not zero is because it has some potential energy which favors it being non-zero. You see, if I put this piece of chalk on the table and I let it go, it falls. It falls in some random direction, right? If I put it exactly vertical, right, with some tiny, tiny change, it will fall in that direction. The Higgs field is like that too, that it's not happy being vertical. Vertical would be zero for the Higgs field. It prefers to fall. Okay, so the standard model is built like that. We call it spontaneous symmetry breaking. the Higgs field switches on, and then it gives everything their masses and charges and other properties. But this energy, the reason it falls, it has energy. This chalk has potential energy if you put it standing up, and it has less potential energy if it's falling down. Higgs field is just the same. That's the way the standard model is built. And so this energy causes it to fall down. Now that energy of the Higgs field actually is the dark energy. That the minimum value of this energy of the Higgs field is actually the energy in the vacuum. When the Higgs field has picked its value, how much energy is there in space? It's that amount. So the standard model sort of is related, the existence of the Higgs field in the vacuum is related to the energy it possesses in the vacuum. Now, we live here, so if we draw, the potential energy is called V. If we draw the Higgs field, then in the standard model, we do that. Okay, so the Higgs field likes to be here at the lowest energy position. The very strange discovery at the Large Hadron Collider is that if you measure the properties of the Higgs boson here, and you then calculate in the theory, the mathematical theory, what is the potential energy at larger values of the Higgs field, you discover it rises, but then it comes down again. Okay? There's another possible vacuum here, which is lower energy than ours. And that's still a puzzle. Why is that true? What does it mean? See, one thing it means is that we may not be stable. If we follow the universe to the future, this can tunnel quantum mechanically, can go to that. And that would be pretty impressive if that happens. So yes, it's related. We still don't understand the connection, but we've got clues, and many, many clues we have now about fundamental properties of the universe, which don't really make sense in the 20th century picture of physics. And again, I may say more about that later. So we're getting these really important clues. Personally, I believe physics is on the threshold of another revolution. You know, in the beginning of the 20th century, there were two revolutions, quantum mechanics and relativity. They were brought about by certain paradoxes, puzzles. You know, there were pieces of tension where things didn't really make sense in the standard picture. And focusing on the paradoxes and the puzzles and the difficulties was very, very fruitful, because ultimately it caused the revolution in physics. Now we have some big paradoxes and puzzles. One of which is that we are certain we came out of a Big Bang, but this singularity makes no sense. In Einstein's theory of gravity, the singularity makes no sense. The singularity means that all of space and all of matter was at one point, one mathematical point. If you only have one point, you can't write down a differential equation. Differential equation means you difference, but at only one point. Okay. You can't difference with anything. So Einstein's theory fails at the singularity. And we just published a paper recently trying to explain this in quantum mechanics, what happens to the singularity in quantum mechanics. So that's a big puzzle in the standard picture. And most conventional theories of cosmology do not even try to address that puzzle. Most people think it's too difficult, and they leave it alone. But to me, it's a big, big clue, and we have to solve that puzzle, otherwise we won't understand anything. And then this dark energy. It's a very big puzzle. What is the dark energy? So that is a huge clue that traditional approaches to physics from the 20th century are incomplete. There probably needs to be a new principle, something like relativity or quantum mechanics, that will explain this dark energy. Let me just say a little bit more about the dark energy, why it's so amazing. You see, the dark energy is making the universe expand faster. What that means is that matter, which is further than a certain distance from us, will be carried away from us so fast that we will never see it, never ever see it. Okay? So without the dark energy, you would say, okay, the Big Bang happened. So imagine that time is vertical and time zero is the floor of this room. Okay? That's the Big Bang, is the floor. And now we're traveling forwards in time. And when we look outwards in space and back in time, we would look out and we'd see more and more and more of the universe. Okay? So however long we wait, just we can see outwards a distance equal to the speed of light multiplied by the time. That would be the distance we see. And if we wait longer, we'll see everything. Long enough, we'll see everything. With the dark energy, it's not true, because with the dark energy, the universe is speeding up in the expansion. So stuff further than 14 billion years, roughly, or more like 20 billion years away from us, is so far, and it's going to be carried away even faster because of dark energy. We will never see it. Never, ever, ever, ever see it. Now, in physics, we learned that if you're talking about something which it's impossible ever to see or observe, perhaps it doesn't even exist. Okay? And so, and quantum mechanics tells us that when you're, certain things, many things in physics don't really exist in a classical description. So we think of the position of an electron, where is the electron? Is that, does it have a single position? No, the answer no. The electron is many places at once. It doesn't have a single position. Typically it's spread in space. And so likewise, when you think about the universe and you realize that most of it we'll never see, maybe you shouldn't even be talking about it. Maybe you should make a theory which doesn't mention things which are undetectable. So that's very challenging. Suddenly, a simple way to put it is we have discovered, because of dark energy, that we live in a finite universe, not an infinite one. It's a very profound change. Okay, and actually for me it's a very hopeful change. It means we can probably understand all of it. That's what I believe. Okay. If it went on forever and ever and we had to wait till eternity to see it all, maybe we'd never understand it. Yeah.
What would you say about human transformation from being monkeys, suspicious, and then a human being created?
Yeah,
that there is no suspicious transform from one to another.
Right.
Just make a kind of adaptation to a new environment. Then it's supposed to be on the same suspicious. There is no transformation from one suspicious to another.
I don't. There's no transformation. I didn't understand the.
I mean, there is no any example
Yes.
here in our life today that prove human on the past transformed from being monkeys to humans.
You say there's no evidence?
Yes, there's no.
No, there's plenty of evidence. There's fossils. There's a lot of evidence.
Just take a look around that some kind of birds, fishes that we found today, it's just transformation with the same suspicious. Make us what we call it a little bit of adaptation.
Yes.
To the environment itself.
It's a lot of adaptation.
Yes, adaptation.
Yeah.
It's not a transformation, totally transformation from being a monkey.
No, I think all the scientific evidence says that life originated on Earth about 5 billion years ago. And the first organisms were very tiny. And certainly they had no intelligence or anything like that. And those organisms evolved into cells, and then there were multicellular organisms, and then plants and animals and so on. So yes, this is a transformation. But evolution is understood as driven by random processes and selection, natural selection, the survival of more well-adapted species. Okay, but you see, even if you accept evolution, to me it doesn't explain why we have the capability to understand black holes 1.4 billion light years away. We weren't adapted for that. Okay, so either the universe is very simple for some reason, that even a poor monkey can understand it, okay, or there's some bigger picture we don't know. Okay, there are deep mysteries here. By the way, you know, one can't really help, when you talk about cosmology, you can't help but overlap with religion to some extent. Because, of course, religion has been telling a story about this for a long time. I mean, these are stories. I would say modern physics is a story. I mean, it's a story, okay? It's a very successful story. But in fact, we had some very interesting lectures last month at Perimeter Institute, where I'm director. We had one of the experts on quantum mechanics. You know, quantum mechanics is the most strange theory we have. It tells you that everything you thought was true is not true. You have to rethink everything, okay? And quantum world is very abstract and very strange. But he began his lectures by saying, the problem with quantum theory is we don't have a story. Okay? What we will tell you is that if you send a particle towards two slits, the particle will go through both, okay? And then interfere with itself in some way as to make a pattern. And he says, I'm sorry, it's not a good story, okay? You see, the mathematics works, there's no question. The mathematics works, it makes predictions, you can use it in technology. All this technology is based on quantum mechanics, by the way. This laser only works because of quantum mechanics. So all our technologies only work because of, modern technologies work because of quantum mechanics. We know that it's right in some sense, but we don't have a very good story about what is going on. So they're very deep mysteries, and they're proposals to interpret what's happening. But physics is physics really makes a revolution when there's a new story. So Einstein told us that space and time are related. That was a new story. And quantum mechanics told us that particles, do not have a definite position and a definite speed. It's impossible. So that is it was a new story. It's not complete, that story, because we can't picture it intuitively. So we're trying to make a story of the universe, right? That's what we want. We will say we've succeeded when it feels right, it works with all the observations, and so on. But the difference between science and the scientific approach and the religious approach, I would say, is one of humility. It should be. Most scientists are terrible. They're not humble at all. Okay? But the scientific approach should be humble. You should say, okay, I make this attempt to describe nature, but I would like to prove myself wrong. And I will work as hard as I can to work out the consequence of my theory, my assumptions, and then I will try to find the experiment that could show it to be wrong. And if it's wrong, I'll say, great, it's wrong, I need a new idea. Okay, so that is being scientific. Actually, not so many scientists are very scientific. Most of them say, oh, it's my idea, it must be right. Which is worse than religion in my view, because we should be humble before nature. So there's some big story going on, that's for sure. The story is miraculously simple in some respects. For example, to describe this whole universe that we see, it's vast, right? It's the biggest thing we know, but it's also the simplest. You can argue that the whole universe that we see is simpler than one atom. Okay? To describe the structure of the universe, we need two numbers. That's it. When I describe the geometry of the universe, the structure, I only need two numbers. I need three to describe a hydrogen atom, which is the simplest atom. The universe is stunningly simple, okay? And that means there should be a simple explanation. And we don't have it yet, okay? And so it's very exciting, because I honestly believe in the next 10, 20 years, we could have some radical new simple explanation of the formation of the universe. The connection with religion, I should say, you see, in a way, cosmologists love cosmology for almost religious reasons, because we think, wow, what a privilege. I can think about this, and some of the ideas make sense. It's amazing. But I think we should take a very humble attitude. There's a lovely book I was just reading by a Jesuit priest. The founder of modern cosmology was a Jesuit priest, Lemaitre. He was very good at math, and so he solved Einstein equations and described a hot Big Bang. And he said, religion and cosmology are like swimming and walking. It's just different. Okay. Both are good activities, but don't try to mix it.
My question is, I need an example that one species transformed to another one.
One species transformed to another?
Yeah.
It happens all the time. Today people can do this with genetic engineering. Mm-hmm. Have you heard about CRISPR? Okay, so this is a technique for changing the genetic code of an organism. And so it's really revolutionized in the last few years. You can take a bacterium, you can take out part of its gene, replace it with another one, and make a new bacterium. And the new one is a different species.
I guess
It's a different species. There's 1 billion species of bacteria, as you know. As you know, it is still a bacterium. It's a different species. You can engineer different species. We can do that.
I'm artificial. I guess this one is.
It's artificial.
I'm just.
If it can be done, the natural world is much bigger than the lab. So all this is going on in nature all the time. When viruses infect bacteria or cells, this is what they do. In fact, this mechanism is the mechanism which viruses exploit to cut genes, to replace them. So there's nothing sacred about a species. It can be changed. We know that. In the lab, you can do it in the lab today. So I would say there's really not much doubt about evolution. It's not really worth debating anymore. I am a skeptic. I'm skeptical. It's good to be skeptical. But at a certain point, you have to say, okay, the debate has moved on. And so there's plenty of data from the archaeological records of different species. Of course, we need more. But I would say just the fact, people who breed dogs can change, as Charles Darwin knew, that you just breed the right dogs and the dogs evolve in a certain direction. You can control that. And in nature, it happens all the time. So So evolution is a very small feature on here. I'm talking about something much bigger than evolution. Okay, evolution happened on a little planet. You know, it's just a tiny thing here. But I was mentioning the Jesuit priest because there's a very nice book I was reading recently by a Jesuit priest. It's called Man's Place in Nature. Okay, now, it shouldn't say man, it should say human. But he was in the 1940s. He had this picture. He's a remarkable individual. He wasn't allowed to publish his writings by the church. Catholic Church said, no, you can't publish this. Okay, but later the books were published and they were very influential. He was trying to understand, he knew a lot about physics, he knew a lot about biology. He was trying to understand what is our place in the cosmos. He knew about the Big Bang because they had the theory by then. And he was trying to picture, you know, what it means that we're in a universe like this. And where will we go? And he has a speculation that ultimately we will understand everything. Okay, about the universe. It's only a speculation, but quite interesting. Okay, it's good to speculate, but it's also good to be clear that it's only a speculation. So,
Sorry, Neil,
yes.
what's your take on intelligent design?
Of course, design is intelligent. The world works. Intelligent design, it's a funny idea. I think it's used to try to disprove evolutionary theory, okay? But, you know, I was going to show you the laws of physics, all the laws of physics in one equation. You know, it's quite intelligent. I mean, the laws of quantum mechanics are certainly very intelligent. The laws of general relativity are very intelligent. Very simple, beautiful, incredible. Where do they come from? You see, I think evolution is a tiny problem. And I think the answer we more or less know. It's not worth debating. Evolution of living organisms and humans and so on. The question is the universe. And if you accept there are laws of physics, where did they come from? Okay, now some people will say, oh, maybe there's a God and they designed these beautiful laws of physics to allow all this to happen. Other people will say, that doesn't really add anything to the discussion. You're just saying we have some beauty and you're just attributing it to some cause we cannot check. I don't know if you've added anything. But there's no question it's a deep mystery. Why does the world work that way? So on the one hand, I would say religious people are correct in pointing at deep mysteries. And if nothing else, it makes us appreciate we live in this magical universe, you know, and our opportunities are unbounded as far as we can tell. You know, if we ask, can we ever travel in space? Can I go to the other side of the universe? The answer is yes. It's not that, in principle, not difficult. Nothing in the laws of physics prevents us from traveling to the other side of the universe, even within a human lifetime. Okay? So when I look at the laws of physics, I go, wow. And I also think, what a future is possible. Okay? And this should be something that brings everyone together because physics is independent of culture or background, geography. You know, Dirac's equation is valid in Japan or in Bangladesh, or it's all the same because we're all made out of electrons and protons, and so I see physics as an incredible cultural unifier. And cosmology, we live in the same universe. So to that extent, that religion is about appreciating the world. I am 100% in agreement. It's amazing. We live in a miraculous world. There's no other way to say it. And physics doesn't explain the miracle. Okay? But when people get dogmatic and they say, no, I have the answer, it must be my way, and then they have no evidence, then I, disagree. But, yeah.
I'm not a physicist, but I just want to know the relationship between the universe and the black hole.
Aha.
Is it that after some time, the black hole will swallow the
Good. So, The first relation is that both of these objects, the universe and the black hole, are very mysterious in Einstein's theory. Okay, so in Einstein's theory, the universe begins with a singularity. All of space, all of matter at one point. It's very strange. And his theory just fails at that moment. He cannot describe what happened. Inside a black hole is just the same. Inside a black hole, when you fall in, as you go into the black hole, you have to hit a singularity. And so again, his theory fails inside a black hole. Now, having said that, the universe is very big. This is 14 billion light years in radius. Approximately, actually, that's not quite true. The age is 14 billion years, but the size has expanded, so this radius is not exactly equal to 14 billion. But roughly speaking, you can say this is 10 billion light years in radius, 14 billion light years in radius. A black hole is a small object by comparison. So typically a black hole forms when a big star collapses under its own gravity. The only thing stopping it collapsing is the pressure due to the atoms which make up the star colliding with each other. They're hot, they have a temperature and a pressure, and that pushes outwards. The pressure pushes outwards, gravity pulls in. When the star releases too much energy, releases most of its energy and light and heat, then the atoms get colder, the pressure goes down, and it collapses. So stars are very small, black holes are very small. These two black holes, for example, a black hole, if you took the sun, our sun, and you collapsed it into a black hole, the size of the black hole would only be 2 kilometers across. 2 kilometers, okay? So it would fit in Muizenberg, right? If you take the sun and put it in Muizenberg, it would be a black hole. Now, these black holes are 30 times bigger and 30 times more massive. They have 30 times the mass of the sun, and they would be 30 times larger in radius, but still only 60 kilometers. So that's actually the reason why this telescope can detect them, because these are 60 kilometers apart. They merge, they're emitting waves whose size, the wavelength of the wave, is tens of kilometers. And so when you have your telescope, it needs to be roughly that size in order to detect the waves. So when you see LIGO, you could see the size is matched to the size of the black hole it is detecting. But it's a long way away. Imagine a 10-kilometer object 1.4 billion light years away. It's very, very tiny. But we can, when these two guys merged, each one had 30 solar masses. When they merge, the final object did not have 60, it had 57 solar masses. It lost 3 solar masses into gravitational waves. It's like we took all the energy in the sun and went bang in 0.1 of a second and released all of it. Then it has to travel a long way, and we detect it now. Yeah?
So I want to ask, with the special respect of black hole, I don't know, is there a possibility in the future that we'll be able to explain the science fiction of time traveling?
Yeah, did you see the movie? What's it, Interstellar? Interstellar, right?
Yeah.
Wonderful movie. So, yeah, that's what they speculate. It may be. I don't think we know. As I say, the problem is these singularities. So we know Einstein's theory is wrong. We're sure about that. It must be wrong because it fails at the singularities. Can't predict what happens. So we need a better theory. That better theory, yes, maybe it could allow time travel. Maybe it can allow space travel over huge distances, faster than speed of light. We don't know.
And can we control the very points wherein we are going to land once we fall into the black
according to Einstein's theory, when you fall in the black hole, you must hit the singularity. You cannot avoid it in a finite length of time. I think a few seconds for a solar mass black hole. You fall inside, and after a few seconds or a few minutes, you hit the singularity. That's it. Game over. Okay? But we also know the theory is wrong at that point. So we don't know ultimately what happens. There's a lot of speculation about this, and it's very interesting speculation, very important. Maybe one day we will use black holes to drive spaceships or time travel. It's very interesting to speculate about these things. There's one idea called a wormhole in general relativity. So the wormhole says, we can picture space and time like this as some material, okay, with time going here and space going there. And so normally we can't travel faster than the speed of light, so it takes a certain time to get from A to B. Okay, you can't travel faster than the speed of light. It means you cannot access these positions beyond the speed of light. You can only access stuff here. But if you have a wormhole, the idea is that I cut a little hole here, and then I draw a tube, and I do this. And then I imagine that the tube is very short. So I could fall into the wormhole, and then almost immediately come out here. Or actually, I should draw it the other way. All right, so there should be some wormhole where I fall in here, and I come out here immediately. And it's possible to make solutions to Einstein's theory which sort of look like that. That would allow you to travel faster than the speed of light. So people speculate about this. There's no clear understanding yet. Okay, let me continue.
You were speaking earlier about this dark energy.
Mm-hmm.
So we're sitting in a time now where dark energy is expanding.
Dark energy is very strange stuff. Dark energy, its defining property is that it's the same at all times and at all places in space. So it doesn't change.
Okay.
It's the one thing in the universe that doesn't change. Ordinary matter, when the universe expands, becomes dilute, so its density goes down. The dark energy is just the same at all times, everywhere in space. It's the same. Doesn't change at all.
And it's causing this expansion.
It causes the expansion.
Okay, and then there's this point at which maybe some things are going to be unobservable. So
Yeah. No, I'm saying that distant things, beyond some distance from us, we will never see them.
So in that picture we had earlier of the grey
Ring.
circle, how do we know there isn't something beyond which is unobservable right now?
We're pretty sure there is. And if we wait, we will see a little bit further. Right? So that's a testable hypothesis. That if I think there's something a little bit beyond the grey circle, I just wait another billion years and see if I see something else.
So when do we get to this finite universe?
Because of the dark energy, what it means is that no matter how long you wait, you will never see beyond a certain grey circle. So the whole observable universe you could ever see is finite, not infinite. That's what it means. It's a very fundamental change.
For us.
For us,
To observe.
exactly, and our descendants. Billions of years, tens of billions.
The universe itself is not then finite.
No, what we can see is finite. That's right. So some people would say, okay, that doesn't matter what we can see. Maybe the universe is infinite, and it doesn't matter that we won't see it. I'm not so sure, because I think if something in principle can never be observed, I'm wondering what it's doing in your theory. It seems like a redundancy of the theory. It's probably you've missed the point. It's like, why aren't there green monsters on the dark side of the moon? We can't see them. I'm pretty sure they're not there. But, okay. So, that's all very well, okay? Science, physics can do amazing, amazing things. They are opening up a future where we will observe the universe, we may be able to travel in the universe. Humankind has an incredible future offered by science. But before we reach it, we need to take care of our people and our planet. And you can make a strong case that science, as well as being constructive, has been destructive in many ways. Just go to any African village or town and see all the plastic bags on the floor. We are polluting and destroying the environment and creating havoc. And as you know, the world has huge, huge challenges which we face right now. Whether it's a financial crisis, the energy crisis, the epidemics like Ebola, whether it's poverty, and all these other crises. We have to make sure that we maintain our species and our planet. And this is always what I think about. Kids in an African village, we all know that very well, and how much they have to offer, and yet how much they are denied. They don't have any chance. Most of them have no chance to learn, to develop their minds, to become anything. By 2050, 40% of the world's youth will be African. Okay, Africa has the fastest rate of population growth in the world, and largely as a result of poverty. And because of that, by 2050, 40% of people under 21 in the world will be African. So if you want to think about the future of the world, you have to think about the future of young African people. This is fundamental to the future of the world. I do invite you to look at the new goals, the United Nations. Just last September, they revised the Millennium Development Goals into the Goals for Sustainable Development. It was agreed last September. These are the goals. They're all great goals. It's actually, in my view, a big improvement over the Millennium Development Goals. No poverty. There's no excuse for poverty today. Industry and the economy are so productive. There's no reason why people have to suffer poverty today. Hunger. Again, agriculture is so productive today in the world. Nobody has to go hungry. Most food is wasted in the world. This is a scandal. We have to change that. Health, education. Here, actually, there's a big improvement over the MDGs. The MDGs said primary school education was the only goal in the Millennium Development Goals. These new goals include lifelong learning. People need to learn throughout their lives, not just at primary school. Okay? That means not just access to university, but to education throughout your life. And so on. Gender equality, of course, fundamental. We still have a long, long way to go to reach gender equality. Achieving most of these goals relies on science, relies on technology. Those are our tools, our most powerful tools to change the world for the better. You can't really see this, but I'll explain the map. I'll maybe switch it off. Can you see that? Okay, so science and technology are critical. We're not going to solve problems of world poverty, hunger, water, clean water without technology. We need it. Let's look where Africa sits. You see, this map shows centers of scientific excellence. These are institutions which are first-rate scientific institutions. The institute I direct in Canada is over here somewhere. It's one of these in theoretical physics. There are hundreds in North America, hundreds in Europe, many in China now, some in Latin America. Look at Africa. Zero. There's not one. This is in mathematics. Okay, there's not one. This website is very interesting. You can look at any field, but in mathematics, zero. Okay, this is a disgrace, and it means that Africa, in my view, will not develop equally unless this is rectified. Sorry, too many. Wrong one? Okay. So what's our goal? Well, we need to put one there, okay, or there. I'll tell you why this is quite promising in a moment. But yeah, there will be the square kilometer array coming, which is a great facility. And we'll see if it becomes a center of excellence. Now let's go back to the origin of mathematics. Okay? Where did mathematics come from? Do you know what this object is? Yeah.
Looks like a bone discovered at Congo.
Excellent. Yes. This is the Ishango bone, discovered in the Congo. Currently, it's dated as 20,000 years old, and it is the first known mathematical artifact, actually relating to numbers. There's an older artifact from South Africa relating to geometry, but for numbers, this is the first artifact. These markings here comprise all of the prime numbers less than 20. Okay, and they're in a complicated pattern which people still try to understand, but these are the two sides of the bone. On this side and on that side, the numbers add up to 61, I believe. Okay, so equal in sum, and then there's some pattern. We don't really understand what they were doing, but it is quite clear they were playing with numbers, right, 20,000 years ago. So mathematics was invented in Africa. Okay, and here it is. This is the Ishango. It's near Lake Edward on the edge of the Congo. By the way, this is a very dangerous area right now. There are lots of militia running around and fighting and massacres and so on. So it's a terrible area, but it's... What? Really? No, no, no. This is the Virunga National Park. It's a disaster. I was in Rwanda last week and there was a massacre nearby here. It's not fine now. Sorry. Okay, so here is the invention of mathematics in Africa. By the way, the the 4 or 5 oldest mathematical artifacts are all in Africa, right? Shango bones. Do you know what this is? The oldest astronomical observatory in the world. It's in Nabta Playa. It's south of Egypt, near to Sudan. It is, I think it's 5,000 BC. Okay? And then, of course, the pyramids in ancient Egypt. And so the laws of geometry and engineering were certainly well understood at that time. And then we have a sort of history of especially mathematics and physics since that time. I'm going to test you all and see how good you are. So who is that? Who is that? A young man. I'll tell you, he's about 24. And he invented something quite important. Scottish? Maxwell. James Clerk Maxwell. Okay. Who's another one? Let's pick another one. Who's that? Excellent. Well done. Emmy Noether, right? Jewish woman, young woman. In 1915, she discovered what energy is, mathematically. Something which Newton didn't know, or Einstein didn't know. Noether solved that problem. Very, very powerful mathematician who was among many, there was a lot of prejudice in her time against Jews, against women. So she was brilliant, She was allowed to teach in a German university without pay. Her whole career, she was never paid because it was considered inappropriate for a woman and for a Jew to teach at the university. She invented a lot of modern algebra. So probably the mathematicians among you know Grothendieck. So Grothendieck attributed much of his ideas to Noether. These are some of the people who played a role in the history of mathematics and physics. Do you know who that is? Dirac, Paul Dirac, discovered the equation which describes 3/4 of the known particles. Right? Electrons, quarks, neutrinos, all obey Dirac's equation. Who's this guy? It's more recent, 1960s. You see, you need to know him. This is John Bell. Have you heard of Bell's theorem, Bell's inequality? It's in quantum information. So he proved a theorem according to which you can do an experiment which in one go will disprove any possible classical picture of the world. Right? So the classical picture of the world means the world is a machine, right? That everything has its place, it might have a speed, and once you define its state, it's like a machine. It will just keep going in that state. That was Isaac Newton's picture of the world. The world is a machine. And once you know its state, you know everything in the future and everything in the past. So John Bell proved that you could do an experiment which would show that no mechanical model of the world could ever explain reality. Okay, quantum mechanics is not a mechanical model because it involves probability, but even more because it doesn't give the state of the world doesn't give the world a definite state at any time. So that's John Bell, and then there are some other people. What I want to talk to you about a little bit, you see, I've talked about understanding the cosmos, the very big things, very small things. But what has impacted technology much more than that has been understanding quantum things. What is quantum? I want to tell you a little bit about the history of quantum and technology, modern technology. Where did it all come from? So who is this person over here? No. You see, you're all educated, right? You don't know anything about history. I didn't know anything about history, I must confess. I went to school, I did my exams, I got A grades in everything. I went to university, Cambridge, I was a professor at Princeton. I never thought about history. Okay? And only when I began to give lectures, public talks about physics, I had to explain, where did all this come from? I had to learn some history. We are so miserable. We don't know our tradition. We don't know where things came from. I show you this, my BlackBerry or laser. We have no idea. We don't tell primary school kids, there is this kind of knowledge. It's a miracle. You can figure it out with your mind and then use it to revolutionize the world. We never tell them that. In my view, that's the most important thing we have to tell them. Who we are. We don't know who we are. Right? As a species, human species, we do not know who we are. This is who we are. We are the creators of knowledge, discoverers of knowledge, utilizers of knowledge to improve the world. We have to understand this. Otherwise, we have got no chance. Right? So that is J.J. Thomson. He discovered the electron. He's an experimental physicist. We couldn't have electronics without the electron. Okay? It's fundamental. So once we knew there exists an electron and we can make it do things, we began. Then, of course, Planck and Einstein discovered quantum mechanics, that the properties of particles like electrons or photons are quantum, Dirac discovered the equation, Schrödinger, and then, who is that? Who is that? A very young man discovered a very important principle in physics. It's a principle that tells us what we cannot know. Heisenberg, uncertainty principle. I think he was 26. He discovered the uncertainty principle. Okay, and do you know who this is? This is the only person to win two. Very good, Bardeen. 2 Nobel Prizes in physics. Okay, John Bardeen. He explained superconductors, and he also invented the transistor. This was the invention, 1947. Here is the transistor. Now, what is a transistor? Transistor is just a tap for electricity. When you go to the bathroom and you turn the tap on for water, you dial the thing and the amount of water is controlled, right? So he and his friends, here's the experimentalist, Brattain, and Shockley was the manager / entrepreneur industrialist. He started the world's first transistor company. These 3 of them won the Nobel Prize together for inventing this very crude device, transistor. Okay, and I can explain how it works, but if you ask. That was in 47. In 1965, people figured out in the space program, NASA space program, figured out how to put 4 transistors into a single device, a few centimeters in size. And then after then, they started putting many transistors into a chip, computers, phones, 100,000 transistors in a single device by 1980, and then recently went up to 10 billion transistors. So in your phone, there are 10 billion transistors. This growth is exponential in the number of transistors. And why do I draw an end? Can you imagine? What if I can make transistors smaller and smaller and smaller and smaller, what is going to limit the technology? What's the end? Can I make a transistor as small as an atom? What goes wrong?
There's no space between them.
Yes, but it's not just that. You see, the transistor is like a tap for electricity, so it relies on a classical picture that electricity is like water, like current, and you can control it. When you get down to the atom, the electricity is made out of electrons. They're not water, okay? They behave in a quantum way. So when you make your wires too small, the electrons will just tunnel. They'll go from one to the other. You have to treat them as they are, which is quantum objects, not classical. So when you reach the size of the atom, you cannot treat the system as classical anymore. You go into the quantum age. But this is the industry that came out of the transistor. That one discovery, and then the ability to put more and more and more transistors into a smaller size, generated this industry. This is electronics. This one is information industry. This one is telecommunications. Okay, and that's the turnover of this industry every year. So can you put a price on the fundamental understanding? What is the price of quantum mechanics? What is the value of it? Right? It's incalculable. I mean, it's at least $10 trillion per year today. But of course, in the future, maybe much more. Okay, so this kind of discovery, the ideas you will be discussing and learning during your time at Ames, these are the most precious possession of humankind, right? Bar none. Their value is incalculable. Quantum. So I think you may take 1 or 2 courses on quantum. It's very mysterious. It's very interesting. This is a classical computer contains nothing but bits, right? So in your computer you have a megabyte. A byte is 8 bits, and mega means a million, so you have 8 million bits. And a bit is just 0 or 1. So it's some physical system whose state is either on or off, 0 or 1, up or down. That's a bit. That's a completely classical picture. It's definite, it's in some state, there's no question about it. Okay? In quantum mechanics, this is a qubit. Now, roughly speaking, a qubit says you can be partly 0 and partly 1. And usually I can't tell. There's some uncertainty. Okay, when I do a measurement, I may get 0, I may get 1. Okay, but it's much more than that. The way to picture a bit, and I won't describe it mathematically, but you should picture a bit as a point on a sphere, like a star on the sky. The position of the star encodes the information in the quantum bit. So there's an infinite number of possible states for a quantum bit, and this is the smallest object which can exist in the quantum world. So roughly speaking, for every bit that a classical computer holds, if I put a quantum bit, I will get infinitely more information and information processing capacity. So for example, if we're able to build a quantum computer, and by the way, right now you can program a 5-qubit quantum computer. IBM has put it online in April. They have a quantum computer at IBM, and you can write a little program and it will give you the results. It's only 5 qubits. Okay? So, but if you manage to make a quantum computer with 200 qubits, well, with 100 qubits, it would be more processing than all the computers in the world today. Okay? And 100 qubits might just be 100 atoms. So you couldn't even see it. It's a very small thing. Okay? And this you should picture as the computing power in the natural world. Right? Every biological molecule is a quantum computer. And this is how it operates. It's processing information all the time. It's infinitely more powerful than all of our computers. So we might be impressed with these laptops today. Okay, in 5 years' time, a laptop will hold all of the books which have ever been written, and articles and everything. Every word that has ever been written by a human being will fit on a laptop. Okay, 5 or 10 years from now. But actually that's nothing compared to what a quantum computer will do. So a quantum computer may completely change the human condition. We will be able to, for example, simulate molecules and chemistry and design drugs, for medical purposes or engineering purposes. Currently we cannot, because it's very hard to do complex quantum calculations. But if you get a quantum computer, that's the first thing you will do, is design nanostructures or molecules, and that will be completely revolutionary. Here's a qubit. Typically the qubit evolves. It's a point on a sphere. It's rotating around. The whole question in quantum engineering is, how do we control these qubits? How do we coordinate them, synchronize them, getting them operating together? And this is what some of the technologies which exist now. There are micro devices in which quantum mechanics is controlled. There are quantum sensors, so you can 3D print diamond today. You can just print a diamond if you don't want to find it. It's quite slow, so you can make only 1 micron layer per day of diamond. But then you can turn that diamond into a super detector that you include impurities in the diamond, like nitrogen atoms, access them with a laser, and this can be used to probe biological materials non-invasively. You don't need to take an X-ray. You can hold this somebody can breathe on it, and then you will detect what are all the molecules in their breath. That will tell you if they have cancer or if they have some other medical problem. And you will be able to collect vast amounts of information very quickly. It will be completely revolutionary in health and many other fields. So this is what's coming: quantum materials, electronics, computers, sensors, communications. This is the future industrial revolution, the quantum revolution. And we don't know exactly when it will happen. It may be 10 years from now, it may be 20, it may be 30, but it's coming. And Africa needs to be ready for it. So I think the first part of this talk, I hope I've convinced you that education, science, and technology hold the keys to our future. I mean, we need to prepare the young generation to be ready for the modern world, for all of these opportunities. And these opportunities are our best hope to deal with all the crises we face. They have to change. I don't want to talk much about this, but I'm sure all of you have experienced inadequate education. Whether it's at school, you're forced to do rote learning, times tables. You have to learn stuff and just repeat it in exams. It's not about thinking for yourself. It's more just repetition to get a grade. That is inadequate. That is not an acceptable form for education. It does not prepare people for the modern world and modern technology, right? And so education has to change drastically to cope with the advances we're making in technology. Science has to change. I believe this very strongly, that ever since science was developed, if you go back to Pythagoras, scientists became secretive. Pythagoras kept his discoveries secret because he knew they were very powerful, okay? And he wanted to protect it. And ever since then, scientists have tended to do that. They live in a world of their own, and a tour ivoire, okay? Many scientists just live in their lab or their university. They want a grant, they want a job. They're happy to do the same research they did forever, okay? And they never explain it to anyone. They just say, oh, it's too complicated for you. You won't understand, okay? Just give me my grant, give me my professorship, I'm chasing a Nobel Prize, okay? I haven't got time to explain it to you. I believe science has to change. We cannot take that attitude anymore. We have to explain to the world, to people, to ordinary people, to people in villages, this is what's coming. This is how the world is changing. You need to encourage your kids to be interested, because otherwise they don't have a future. Okay? So I believe education has to change, science has to change, technology has to change. Technology has very often been used for war, for terrible things, still being used for terrible things. That can't go on. We're in risk of destroying the whole planet and ourselves and making it unstable. We have to control it. And every scientist needs to be aware of their responsibility to change all these things. We have to connect our science to our humanity. We're human beings. We live in a very special position in the universe where we can understand the universe. And we have to use that responsibly. We have to remember who we are, understand who we are, and not just say, I'm a scientist and I will work for whoever pays me and I give them whatever they want. Okay? And it's not my responsibility. No, that's got to change. Africa can lead in this, right? Africa is just entering science. Ames is one of the vehicles. Africa is almost non-existent in science, but it's going to become Very important, because all the young people are going to, a lot of them are going to be African. A lot of them have to be interested in science. Africa can lead in making science connect to our humanity, connect to people. That's why we started Ames in 2003. Here, where you are, there's a long story attached with this. This hotel was derelict, okay, was abandoned, and we managed to buy it for a very cheap price because we had no money. And so Ames' story is very interesting, and you will learn that as you are here. Above all, it's an African institute. It's dedicated to the future of the African continent. As you know, Pan-African student body, we try to bring outstanding lecturers. Only the best is good enough for Africa, that's my opinion. Africa has to catch up and overtake. We can't waste time. Second best is not good enough in anything. So we try to get the very best lecturers. We call this 24/7 learning environment. You shouldn't sleep well here. Okay, none of us should sleep well. We've got a lot to do. We haven't got much time. So coffee is the answer. We have to help each other. We have to energize each other, encourage each other. You know, I always think, I want to be the next Einstein, okay? I want to understand the Big Bang. But most of the time, I also want to be realistic, okay? So if I spend some of my time doing research, my own research, thinking, it's my private time, I need to think hard. But also spend some of my time helping others to think. If I can help hundreds of other people try to be the next Einstein, I'm more likely to succeed. In the end, it will be random, right? In the end, somebody's going to get lucky and discover what is dark energy or what happened at the Big Bang. It may not be me. Do I care? Not really. I don't care. I want it to be discovered because I think it's important for humankind. But do I care who it is? Not really. It doesn't matter. And so if I can help anyone to do that, it's time well spent. So always think of your time as being partly for yourself, your personal development, but partly for everyone else around you. Then you're just using your time well. This is our slogan. We want Africa to be rich, so everything we do must be relevant. We don't want to be sitting in an ivory tower. Relevant, I mean very broadly. Relevant means exploring the future, okay? But it needs to be important, innovative. Don't follow traditional approaches. They'll never get you anywhere. If you just do the same thing, you're like a machine. Why bother? Somebody else could do it. You have to try doing things in original, new ways. When you try to solve a problem, try to say, I'm not going to do it the textbook way. I'm going to invent a better way to solve that problem, a new way. Cost effective, we don't waste money here. If you learn not to waste money, you will get more of it, okay? If you waste money, it's gone, finished, you'll never get any more. So, and this is the most important thing. All of us at Ames try to operate in a high quality way. That means being good to each other, means setting a very good example in everything we do. That's when we started, 2003, Ames South Africa. 2008, we declared that we wanted to make a network across Africa. In 2011, we started Senegal, 12 Ghana, 13 Cameroon, 14 Tanzania, and then this year, Rwanda. Okay, so these are all the African countries. Here is Thierry Zomahun, our president and CEO, meeting President Kagame in Rwanda. I was there last week, and absolutely amazing things are happening there. Here we are. The Ames Secretariat is in Kigali. It moved from Cape Town to Kigali. 2 weeks ago, it moved into a new building, very nice building. And here are the staff. And you see what we're doing? What is it? Bolt. Bolt. Okay, so Bolt is my hero. And along with some other people, but he's one of them. And I want to tell you a little thing about Bolt, why he's so important. Jamaica has 10 men who can run under 10 seconds for 100 meters. The USA has 2. Okay? Jamaica won 100 meters, 200 meters in the Olympics in men and also in women. How did that happen? Jamaica's a tiny country. How did that happen? Tell me. Is it genetics? Maybe they all came from West Africa and everyone in West Africa is really strong. Was it the slavery? You know, they came across in boats and only the strong ones would survive. Most of the slaves died. Okay? So what's the explanation? Everybody's speculating because the US is in the shadow of Jamaica right now. Okay? And people are speculating. But Jamaica has the best coaches in the world. This is one answer. They have 10 top athletics coaches. But even more important, every year in Jamaica they have a track and field meet in Kingston where the best school kids come to run. And for 3 days, everyone takes the day off from work and they all go and watch. Okay? That stadium is packed with people wanting to know who's the next great sprinter, a 12-year-old. That's how Bolt was discovered. It's in the culture of Jamaica. Sprinting is the thing. Okay? So my slogan in Rwanda is we need to make Rwanda the Jamaica of science. Okay? It's a poor little country. It doesn't have much, but it is very focused, very organized, very strategic. And if that country can succeed in encouraging kids and young people to get into science, there's no reason why it can't become a Jamaica. So we're doing the Bolt dance, and these are all the people who are working for you. Here's Thierry. Here's our new Chief Finance Officer, our new IT Officer for Ames Rwanda. There are 2 Ames alumni, these 2, who are tutors at Ames Rwanda. I think one of them graduated from here. You probably recognize. Which one is it? This one?
No, the other one.
This one? Okay. This is the new IGSAN for Rwanda. Okay. So here are all the staff. They work very, very hard. They're trying to raise money. They're trying to organize management, finances, and so on. This was the Ames Ghana graduation last year. There are many other graduations. You can see all this on the Ames Next Einstein website. And there's a Flickr feed with all the latest photos. I encourage you to go and look at there. It's always developing. Ames so far, 1,200 alumni, 250 plus enter this month. 30% are women. We don't go below that. Half continue to PhDs. 2/3 currently working in Africa. 3,000 applications this year. So congratulations to all of you for making it here. And we have 6 centers so far, these countries, and our goal is 15. Okay, so we want to have 15 by 2023. And so we're moving very, very fast, but very carefully. Our claim, our slogan is we want the next Einstein to be African. Okay? We have to aspire to the tops. But more than that, we want to be better than Einstein. Africa provided the world's greatest leader of the 20th century. Okay? I believe that's not in dispute. What we want are people who are both Einstein and Mandela. who are not just intelligent but also wise. Actually, Einstein was quite wise, but unusually wise for a scientist. Many scientists are not very wise. They are very narrow, they're so specialized, they just do what they do, and they refuse to think about anything else. That's not acceptable anymore. We have to connect science with humanity, and that's why I think we need an Einstein who's also Mandela. And that's probably what they will look like. They may be a woman. I hope it's a woman. This is actually an Ames alumna who came here. She's from Swaziland. Some of you know her. She was a tutor in Ames, Ghana. And guess what she works on now? What field?
Physics.
Yes? It's the hardest field in physics. What is that? Pardon?
Technology.
Excellent, yes. She's working on quantum gravity. She's at Perimeter Institute, and she's working on quantum gravity and the nature of space-time. I want to tell you about, we have 1,200 alumni. Each one of them has an incredible life story. And I've just spoken to very few of you, but I already know that many or most of you have incredible life stories. You've had to struggle. You've had to overcome almost impossible adversity. Okay? And all of these 1,200 are similar. And that's where we draw our strength from. We draw our strength from where we come from, who we are, and our determination to show what Africa can do. Okay, so never forget your roots. In my own case, the best thing that ever happened to me in my life, you know what it was? Both my parents went to jail. Okay? That was the best thing. Why? Because they went to jail for the right cause. They went to jail for fighting apartheid. And through their experience, through their struggle, they became very inspiring human beings. And through that struggle, 30 years later, the world changed. And democracy came to South Africa. Both my parents went into parliament. And that's where I come from. Okay? So I learned from them. If the whole world is against you, or almost all of it, if all the powerful forces are against you, don't give up. If you're right, you'll win. You need to be clever, you need to be strategic, you need to be principled, and you can overcome anything. Small number of people can overcome anything. That's my experience, that's where I come from. That's what gave me the courage to start Ames. Almost everybody I knew said, this will fail. You haven't got any money, you're not established university, you're going to compete with UCT, they will squash you like a fly. Okay, so everybody made negative predictions, but somehow I knew this is possible. So I want to tell you just one quick life story, one of our alumni. This is Martial. Here he is as a child in Cameroon. Some of you know Martial. Yeah. So he's one of our alumni. I had the privilege to visit his mother. His mother was a single mother. Father left. Father became an alcoholic and left. So single mother raised 6 children on her own. She built her house with her bare hands. She got a piece of land nobody wanted in Yaoundé under an electric pylon. Nobody wanted to live there. So she took it and she built the house with concrete blocks for her 6 kids. She's a market trader. She's not educated. But she raised the money for all 6 kids to go to university. They all went to university. Okay? I had the privilege to visit her. She cooked me dinner. And I was completely blown away. This is somebody stronger than I had ever met. Somebody more determined than I ever met. And I said to her after dinner, how did you do it? Where did you get your strength? And she said, the Lord. Okay? So when people disrespect religion, I don't. people draw strength from it. And you know this. Incredible strength, and often for very, very good purposes. And so I respect it fully. And she is still my hero. I cannot imagine surviving that. I would have given up, right? I would have said, life's not worth it. I prefer to die than to struggle. She wouldn't. She refused to give up. Amazing. And Africa's full of those stories. Again, that is the source of our strength. When we look at people like that, who had no opportunity and yet gave their children this amazing chance, we have to live up to their example. Okay, so here's Martial as a child, and here he is today. So he is a permanent staff scientist at Yale University in the US. He is one of the leading mathematical epidemiologists. He studies disease and propagation. He publishes, here he is, Martial in Deformbar. He publishes papers in the National Academy of Sciences of the US. He was one of the main advisors to West African governments on the Ebola crisis. He went to West Africa, he studied the spread of the disease, the effectiveness of interventions to stop it. He made mathematical models. He's an excellent mathematician and had a very big impact. Okay? Besides which, he devotes a lot of his time to helping others. He goes to Brazil to teach in the slums for his church, by the way. He goes every year for 3 weeks or a month to teach in the slum kids. And he wants to start a research institute in Africa into epidemiology. So all of his research is into neglected tropical diseases, schistosomiasis, TB, and so this is what he's done. He sets, again, amazing example. I could give you hundreds of other examples of our alumni who, in fact, the book is coming out in November. There's going to be a book of the stories of 100 Ames alumni, their life stories and their hopes. This is what's coming. I mentioned in Africa, there's this huge facility. At least in astrophysics, Africa has an amazing chance, right? 5 years from now. And we have some cosmologists and astrophysicists here. This is what's coming to Africa. It's in our hands. This facility may just be a facility for Western scientists, right? Africa can put a lot of the money, Africa can operate it, and then people from the US or Europe will come and take the data and they will do all the science, right? Or Africa can grow its own astrophysicists. And of course that's happening in a small way. It's not enough. Africa needs to go quickly to rise to this opportunity. This is my slogan in cosmology, right? 30 years ago, when I started working in cosmology, we knew nothing. Every number, there was one number we knew to better than a factor of 2. That was the temperature of the universe. Every other number we didn't know to better than a factor of 2. We didn't know the age, we didn't know how fast the universe was expanding. So we were in the dark ages when I started cosmology. And what we've learned in cosmology is we will see much more than we expect, okay? That nobody would have predicted how much we have learned about the universe today. So my slogan in cosmology is "we shall see." And then of course when people ask this question, is it true? Will the next Einstein be African? My answer is just the same, we shall see. Okay. So, thank you.